Welcome to Lecture 9. In this lecture, we wrap up our discussion of energy and energy conservation. The first lecture section is an excerpt from Physics 4A lectures, looking at what sets conservative forces apart from non-conservative forces and how the predictable nature of conservative force allows us to store energy using it. At this point in the semester, only the gravitational and the spring force are conservative forces. And the next lecture section looks at the forms of potential energy involving these forces. I think energy, even mechanical energy, is quite familiar idea to most of us in one sense, but the concrete way we are handling it might be a bit different from how you have formed your intuition about energy. So I encourage you to use PhET simulations to help develop your intuition. The third lecture section shows an illustration. Finally, we wrap up with a couple sections looking at homework questions relating to Chapter 3. As a reminder, please be mindful that there has been a shift in chapter and section numbers between our old CNX version of the textbook and the LibreText version of the textbook. Although the screens from the videos will say Chapter 4, these are the Chapter 3 questions that you will see. Thank you. After this lecture, we wrap up this week with our coverage of momentum and collision analysis. All the forces that we have been describing, we have talked about different types of force: gravity, normal force, tension force, friction force, and there's, I thought there was some more, spring force. All these forces that we've been dealing with for application of Newton's law. So we want to categorize those forces into two different distinct categories. What we are going to call conservative force, and what we are going to call non-conservative force. And I think this is the example we ended the class with last time. I gave example of one conservative force, gravity. So if you have a ball and I throw it up and it comes back to my hand, this is an illustration of how gravity is a conservative force. Do people remember? Yes? We did end the class with this on Tuesday. And I used the example of friction as an example of a non-conservative force. So when I push this cart on its side, not on its wheels, when I push it this way, then so as this cart comes to a stop, that's an example of how friction is a non-conservative force. And I don't think we got to, we ran out of time there, so we didn't have time to talk about what makes a force conservative, what makes it non-conservative. Good. So let me write down those two examples on the board so that we have something concrete to think about. So gravity is an example of conservative force, and friction is an example of non-conservative force. Let's go through more examples and try to figure out if they're conservative force or not. So let me write down the whole list of all the different types of force we've been dealing with so far. We've been dealing with gravity, friction, and we have a few more. Tension force, spring force. Anything else I'm forgetting? Normal force, thank you. Normal force. Anything else? I think in terms of types, this might be it. Let me just write down one more as a category of sort of applied force. So let's try going through each of these and see if they are conservative force or non-conservative force. So gravity and friction, we already put them into these two categories. Tension, is tension a conservative force or non-conservative force? A lot of people think it's conservative because you are thinking of this. I have a pendulum, or I'm going to have a pendulum, and so here tension force is in action, right?
And this was one of the examples of conservation of energy I used on Tuesday. When I hanging to the side and let go, so tension force is acting the whole time, and you see the energy being conserved. So you want to associate this with the conservative force, right? That's where your intuition is coming from. What I want to tell you is that tension force is actually not conservative force. Let me illustrate. So I can actually put more energy into this ball using nothing but tension force. Right? I mean, so my hand was moving, so you have that. But the way that force was applied to this ball is through tension force alone. So on this ball, nothing but tension force is acting. But using nothing but tension force, you can change the energy of the ball, which means this is not really tension force is not a conservative force. So let me put tension force down in the second list here. What about spring force? So spring force, so I guess, yeah, so you're used to thinking of spring force and tension force being similar. They are different in one particular way. So if I hang this here, if I hang this here, and there's tension force acting on this somehow, and if I hang this spring here and hang a little bit of mass there so that it's not just a spring. So in many aspects, these two forces, you're used to thinking of them as similar. They are both a pulling kind of force. But there's one important way in which tension force and spring force are different. Can anyone tell me what that one important way is? So with the spring force, there's a mass. But I could have hung, I could have hung another mass here. So it's not a matter of how much mass is hanging there. But actually, as I'm doing that, maybe you will notice something. So let me hang more masses here. So I'm going to hang more masses here. Watch what happens to the string here. And let me hang a little more mass on this spring and watch what happens here. Do you see an important difference between the spring and the tension force? What's one important difference? Yeah. With the spring force, you see the change in length. So with the spring force, you have a way of telling how much force I'm applying. In fact, we haven't gone into detail about the spring force, which we'll do later today here. But the way I've been using spring so far in class was I was using this to illustrate how much force I was actually applying. So that's one important difference between spring and the tension force. With the tension, no matter how much force I'm applying, you won't really see it. I mean, the string might break at some point, but until that happens, or until it goes completely slack, you can't tell from this picture if how much tension force there is. And that will be an important distinction when we actually go into what makes a force conservative and what makes it non-conservative. So with the spring force, let me put it in the category of conservative force. And we'll see that the property I was pointing out here will be important in determining why spring force is conservative, whereas the tension force is not. All right, two more forces. Normal force and applied force. I guess one of the ways I would apply force is through normal force, but so normal force. Is normal force conservative force? Yeah, so a lot of people so normal force and tension force, I think the intuition that a lot of people have for these two forces are similar, in that you see these forces in a lot of contexts where energy seems to be conserved. So you associate with this energy being conserved, which is not wrong, as in, let me give you an example involving normal force where energy is conserved. So I have these tracks. So when this ball is on this track, there's normal force between the ball and the thing, right? Now, if I start the ball here and let go, then the motion you see, well, I mean, it's going down because of friction. But imagine ignoring friction. When you imagine ignoring friction, then the motion you see is consistent with the conservation of energy. Right? So that's why a lot of you would want to associate normal force with conservation of energy. But watch this. I can actually put energy on this ball using nothing but normal force. Right? So normal force can be used to put energy into this ball. And what that means is normal force is also not a conservative force. And when we get to the actual criterion that makes a force conservative, you will see that more easily. So normal force is not a conservative force. And the final applied force, I'll just give you a quick description. It's a sort of, what I mean by applied force is force like this one. I have this cart here right now, right? And right now, there's gravity and normal force acting on the cart. Its energy is not changing. When I say apply the force, I mean, really apply the force. Like if a question tells you a force F is being applied on this cart, either by me pushing it, or it could be by me, using friction. So there are different ways I might be applying the force, but the idea is that there's some particular force that's specified on this cart. That's not given by that's not necessarily from one of these forces, but the problem simply tells you there's some external applied force of force F. And when you look at this example here, applied force also doesn't conserve energy here. This cart right now has zero kinetic energy. And once the cart, so it starts moving because I'm applying a force. So when it starts moving, then now it has non-zero kinetic energy. So any kind of applied force would also fall in the category of non-conservative force. So applied force. So we have these two big categories of force. And so I should tell you this now. Actually, these are the only conservative forces you will see in this class. There are no other conservative forces you'll see in this class. So what I want you to go over was, given that this short list of forces is conservative, why are these conservative forces? What's the criterion that we use for saying that a force is conservative versus saying that a force is not conservative? As you think about that, I want you to think about the example we used on Tuesday. So example of friction and gravity. It's a simple example. It sort of helps you think about what it means for this to be conservative. So here's the sense in which friction is not conservative. When this cart, let me have it start out with some kinetic energy. I push it. So it's moving. Let me actually do this with a block. I think it's safer with a block. I keep worrying that the cart will fall over. So when I push this block, it starts by moving, but then it quickly comes to a stop. What would you blame for this coming to a stop? Friction. Specifically, what does friction do that causes this to come to a stop? Well, friction actually doesn't resist applied force so I apply force for a very short amount of time, and for the rest of the time, I'm not applying any force. So the friction is not resisting applied force. Steven, you're going to say something? So friction force is what is converting the kinetic energy into thermal energy, yes. What's the mechanism for that happening? The thing that we introduced on Tuesday, you had a whole lab about this. Work? Yeah, work. So we say that the friction was doing work, and recall from Tuesday that the reason work is important is it ties into change of energy. In particular here, change of kinetic energy. So as the block is moving from left to right, friction is acting to the left. So the force times displacement is negative. It does negative work. It takes energy out of the block. Yep. So you could point to that and say, that's why friction is not conservative. So friction takes energy out of the block. Now, if you stopped there, then friction and gravity doesn't look all that different. When I throw this ball up, if you stop the motion right here, this is what you see. As the ball goes up, what kind of work is gravity doing? Gravity is doing negative work. So look at the motion of the ball. Is what you see consistent with the gravity doing negative work and taking energy out of the ball? Right? So up to this point, gravity and friction, they don't look any different. They are doing negative work. They are taking kinetic energy out of the object. The distinction between gravity and friction is what happened next. So with the gravity, from this point on, what kind of work is gravity doing? Positive, it's moving downward, and gravity is still pointing downward. So the kinetic energy that was lost on the way up gets returned to the ball. What about with the friction? What happens after this block comes to a stop? Yeah, nothing happens. Wait, what happened to the friction force? Right now it's 0, right? So the kinetic friction force that used to be pointing to the left, it's no longer there once the block comes to a stop. And that's the key distinction between a conservative force and a non-conservative force. And the way I like to describe it qualitatively is that conservative force is predictable. As in, you can rely on it. You can predict what it's going to be, so that when a conservative force does negative work, as this ball goes up, conservative force does negative work, we have some reason to believe that that negative work is not simply wasting the energy. That negative work that was done is stored the kinetic energy into some other form. And because the gravity is predictable, it's pointing downward, constant, I have a reason to believe when the ball comes to a stop, gravity doesn't go away. It continues to point downward. So this ball, as it now moves downward, gravity starts doing positive work. It returns the energy that it stole in the first place. So that's really what makes a conservative force conservative. We call it conservative because whenever conservative force does negative work, we don't look at that negative work done as being energy lost. We associate conservative force with potential energy. So whenever a conservative force does negative work, we don't look at it as being lost. We say when conservative force does negative work, that amount of energy that's taken out by the negative work is stored as potential energy. So this is the expression that we'll use to derive a couple forms for potential energy. So in the lab last Tuesday, you guys were using this formula before I had a chance to derive it. So we'll derive this today, and we'll look at the other form of potential energy, spring potential energy. So whenever with the conservative force, this is what you can say. So this is a new form of energy that we are now identifying and deriving formulas for. We say that the change of potential energy is given by the amount of work that's being done by conservative force. So I would call this negative work done by conservative force. Does it make sense that there's a negative sign here? Yeah, when a conservative force does negative work, do potential energy increase or decrease? Increase, right? So when this is negative, I want the change to be positive. That's why there's a minus sign here. So you could write this out as the change in the potential energy is the negative of the conservative force, dot product with the change of position. So with the gravity, I guess it's easier to see that gravity is predictable because we do this every time we solve a Newton's law question. We say, gravity is always downward, always mg. So in fact, when we so let me derive this formula now. So using this expression here. Let me give you a slightly more interesting scenario. Imagine I have a slope where I'm raising a block is somehow being moved from this lower position here to a higher position here. Somehow it's being moved up here. So the block starts out at some height. Let me call this initial height equals 0, just to make it easy for myself. Right? No reason to introduce unnecessary numbers. And when the block goes up here, let me say this final height is capital H. Yep. So this is a situation that we know how to analyze. If a block is moving somehow from here to here, then let me make things easier to think through and say that it's almost at rest every single time. Like it's not moving up the hill because I gave it an initial push and then let go. It just starts out at rest, and I'm just pushing it up slowly, so that slowly it reaches the top here. So when you think about the situation, visualize it. What you should realize is that there must be at least 2 forces acting on it, right? Yes, because there's gravity pulling it down, mg. If that's the only force acting on it, then it's gonna move downward, right? What are the other forces acting on this box? There's normal force, but when you draw the normal force, that's not enough. Because if these are the only forces acting, it'll slide downward. So what else is there? Yeah, there's applied force. So I must be applying some amount of force to make this block slowly slide upward. So there's all this picture in the background, but what I want you to pay attention to right now is the work being done by gravity. How much work is being done by gravitational force? So I guess the easiest thing to do is actually just go through the math and calculate it. So we want to calculate this expression here, dot product between the conservative force, gravity, and the displacement. The displacement vector here would be something that looks like this. This would be my displacement vector. Yeah? Let's just try applying the definition here and see what we can get. So to apply the definition here, let me copy the figure into clean area here so that I can label things better. So gravitational force vector, mg is downward. Displacement vector, it's going this way. Let me label a couple other things that really should have been specified in the question. Somebody should have told you this angle theta, and somebody should have told you, well, I guess that's it actually. Yeah. So to label that angle theta here, I need a horizontal here, and this would be theta. Yeah. And so this is what the definition tells you, that work done by gravity is equal to force mg as a vector, dot product with the displacement. All right. I guess there are different ways to do it. Let me just try applying the definition just straightforward. Like it says, that mg cosine theta. So let me just do that. Mg, so that's the magnitude, times the distance, delta x, times, when it says cosine theta, is it this theta that it's talking about or a different angle? Different angle, right? It's talking about this angle here. Angle between the two vectors. So let me use a different symbol for this, phi. So it's mg delta x times cosine of phi. I want to express this in terms of theta. In the interest of time, let me do this using some numbers. So you can use angle addition formula to do this purely algebraically, but I think I can illustrate my point better if I use specific numbers. So let me do that. Let me make the numbers easy for myself. I'll say theta is equal to 30 degrees. That will also mean a couple of things because it's a special 30-degree angle. Height h is equal to delta x over 2. Like, I have those nice numbers. So, so if theta is 30 degrees, what's phi? Phi is 90 plus 30, so 120 degrees. Anybody here happen to know what cosine of 120 degrees is? Negative 1/2? Yeah, negative 1/2, right? So when I plug in these specific numbers here, then I get mg times delta x times minus 1/2. And let me plug in what delta x is in terms of height h. So delta x in terms of height h is mg. So I have expression here. So it'll be 2 times the height times minus 1/2. So for this particular value of angle that I have used, the expression you end up with, work done by gravity in this situation, is equal to minus mgh. And what I will state without proving it, to prove it, you have to use the angle addition formula, is that this relationship will be true no matter what angle you use. And this is actually one of the properties of dot product that I didn't have time to get to on Tuesday. The dot product takes the projection of the vector. So when you take the dot product between this displacement vector and this vertical vector, the component of displacement that matters is the vertical component. It's this vertical component that matters, and that's just the height h. And it works for all other angles that you might use. So this is the work done by gravity. You use it here to derive the change in potential energy, gravitational potential energy. So change in gravitational potential energy is equal to minus of all this work done, minus mgh. So these two minuses cancel. And so when there's a change in height of h, change in gravitational potential energy is mgh. And that was the formula that you were using last time. And so that's why you care about the change in height alone, not change the entire distance that you travel over the ramp. Does this example make sense as the potential energy that gets stored as a result of the negative work being done by gravity? Yes, no. And here the confidence is this. So as I'm pushing this up, gravity did all that negative work, taking out kinetic energy that might have gone into the box. The confidence here is this. When I let go of the box, then the box will roll down on its own. So to give you an actual physical example, I have this ramp. So when I have this incline of the ramp, so as I apply a force to push this up, without gravity, when I'm applying force, it would have accelerated upward. But because gravity was constantly pulling it down, it didn't gain all that kinetic energy. So even with all my push up here, it ends up with a 0 kinetic energy. But this is the confidence I have from the fact that gravity is a conservative force. That when I let go of this hand, gravity will continue to act, and it will turn the energy the potential energy that's here into kinetic energy. So I don't have the confidence with the friction. With the friction, if as I was pushing, friction took out all that energy of work that I'm doing, so it gains no kinetic energy. I don't have the confidence that when I let go of my hand, friction will snap it back to where it came from. Like, friction doesn't do that. So that's the key distinction between conservative force and a non-conservative force like friction. And so when you are dealing with a conservative force, You calculate the work done, and you say that gets actually stored into this form of energy because you think you are going to be able to get it back. It's a difference of lending money to a friend who's never paid you back versus depositing your money into bank. Like when you deposit into bank, you think you're going to get it back. So it gets counted as your net worth. But if you're lending money to someone who's proven unreliable, then you don't count it as your net worth because you don't think you're going to get it back.
In this video, we will talk about potential energy and a couple different forms of potential energy that you will see this week. So in the video that I borrowed from Physics 4A, you have already seen me discuss the idea of conservative force and non-conservative force and how conservative force is different from non-conservative forces. And at a conceptual level, you could say that the difference is conservative forces store energy, whereas non-conservative forces, they don't. So when a conservative force does negative work, taking a kinetic energy from a system or an object, you have some way to be sure that you are going to be able to get it back. That's what it means when I say conservative forces store work or energy. And there are some mathematical properties that go into that. Your textbook does mention it, work done depends only on the start and the end points. That's a consequence of whenever a force is a function of position alone. So when you look at non-conservative forces like normal force, tension force, applied force, and friction force, usually things that are other than just the position that the force depends on. That makes the force unpredictable, and that's where I say at an intuitive level, conservative force is a predictable force. And the energy that gets stored, it's the work done against the conservative force. So when you look at a situation like this, if you calculate the work done by the conservative force, as in not the work done by the applied force, because sometimes the applied force just won't be there. The object might have some kinetic energy that can be turned into potential energy. So when you look at the work done by conservative force, in situations where energy is getting stored, you will see this work being negative because it's taking energy out of the kinetic energy. So in our way of accounting, the way we account it, keep track of numbers, is we say the minus of the work done by conservative force gives us the change of potential energy. So if a conservative force does negative work, meaning it's reducing kinetic energy, that becomes a positive change in potential energy. And I guess we don't really use this idea that much because this is the kind of what you use to derive the formulas for potential energy, but we won't be doing those derivations. It gets all quite mathematical. So now, having introduced the potential energy, we can talk about conservation of mechanical energy. So I think this is probably best to illustrate with some help of simulation. So I'll do that more in a separate video. You have already seen me use a pendulum-like setup to illustrate conceptually the idea of energy conservation. In fact, that's where we got our motivation from initially. And with the help of simulation, I think I can illustrate more concretely the situations where not the total energy, this is really the total mechanical energy of potential energy plus kinetic energy is conserved. And I added the term mechanical, recognizing that sometimes I might forget to, is because this is not all forms of energy there is. There's like thermal energy, chemical energy. There are other forms of energy that's not potential or kinetic energy the way we are describing them right now. So if you look at the total mechanical energy, if you have non-conservative forces acting, you will see total mechanical energy change. And I will also illustrate that in the simulation. So in a system with only conservative forces, meaning all the forces that might be doing work are gravity or spring force. All the other forms of forces you have seen are not conservative force. In such a situation, the sum of potential energy and kinetic energy will be constant. And that's what we are talking about when we refer to conservation of mechanical energy. So in most situations, it amounts to is friction doing any work. Recognizing, as you saw in the previous video, that normal force and tension force are also not conservative forces, but in most arrangements, like in this pendulum setup, it's set up in a way where tension force is acting in a perpendicular direction to the displacement, so it does no work. So usually you don't have to worry about tension and normal force. But watch out for that. I probably won't give you any such tricky situations. So let me just spell out the common forms of potential energy. Because I don't think I do this in any other lecture videos other than maybe a brief mention in the overview video. So let me just give you this form so that it's stated somewhere. The gravitational potential energy, the most common form and possibly the only form you will see in this class, is given as mass times gravitational acceleration times the height. And it comes straight from what I was describing earlier, that change of potential energy is equal to minus of the work done by conservative force. So as you imagine this guy lifting this boulder up, the gravitational force, I'm just going to draw the gravitational force, not the applied force. The gravitational force is acting downward with the magnitude mg. So if, as you imagine, this boulder undergoing this displacement of height h, from the bottom to the up there, I probably should actually draw this from center of mass to center of mass. So this is the actual height change it undergoes. Or we should make this bottom the reference. Something about consistency. This really matters more if you're doing lab and you need to be really quantitative. So as it undergoes this height change, you can see the force and the displacement being in opposite directions. So the work being done will be negative, and the magnitude of that negative work done will be the magnitude of force, mg, times the height change, h, and this is the potential energy, or if we are dealing with the actual signed quantity, then this the amount of work being done will be minus mgh, and take this whole thing, multiply minus 1 to it, that gives you the change of gravitational potential energy, which is equal to mgh. Now, as you see in this description, this particular expression relates to this approximate form of gravity that applies near the surface of Earth, where you can say g is approximately constant at 9.8 meter per second squared. If you are dealing with like orbital mechanics where things might be moving great distances, then you would have to basically redrive the formula using the universal law of gravitation, which says, let me write down as a reminder, is the universal gravitational constant times the product of the masses, small m and big M. Big M would be like mass of the Earth, divided by the distance squared. That's the inverse square law of universal gravitation. And with this different form of gravitational force, you'd also have a different form of gravitational potential energy, which I will write down the form. I don't think we use it anywhere in the class, because we don't use it anywhere in the class, but I think you might see a similar form later when we do electricity and magnetism. Although it's possible at the conceptual level we won't ever really use this expression. So the universal gravitational potential energy is given by minus gravitational constant times the product of the masses divided by the distance, not squared, just the distance. This comes from like doing integral, applying this definition in a calculus way. This comes from a specific convention where gravitational potential energy goes to zero as the distance goes to infinity. So I thought I would just mention this, but I don't think we ever really use this in the class. All the everyday situations that you might see some in homework questions will be covered by this much simpler looking expression. And the other form of potential energy, which we won't work with a lot, but you will see it in the simulation, and you should at least know the form of it. The elastic or spring potential energy is given by 1/2, this factor comes from calculus, or I guess you could also look at the area under the curve, and the curve looks triangular. 1/2 times the spring constant, k, times the displacement x from the equilibrium squared. That gives you the elastic or spring potential energy. And I don't think any of the homework questions actually use this. There's one question that basically asks you to recognize this as the form of the spring potential energy, but a lot of the conceptual things we'll talk about will use gravitational potential energy. But if you go on to take a physics 4A or more quantitative science class, spring potential energy really comes up in a lot of situations, both in situations that deal with actual literal spring like this, and situations where there is no spring, but the kind of the form of a spring force, it's the form that we use really commonly to model any complicated arbitrary forces that result in stable equilibrium. So those are the two common forms of potential energy, and when we get to electricity and magnetism, you will see additional conservative forces, so additional potential energy forms that we probably won't spend a whole lot of time on. So yeah, this is the discussion of conservative force, potential energy, and two specific examples of potential energy that you will see a little bit as you work through homework questions. And as I said, we'll look at the conservation of mechanical energy and some of the things you can see with the help of a simulation. So we'll look at this middle portion in detail in a separate video using PhET simulation. Bye. In this video, I want you to look at some simulations from the PhET website, phet.colorado.edu. Some simulations that are relevant to the energy concepts that we are looking at this week. So I'm starting from the PhET homepage. You go to simulations, physics, and for the simulations I'm looking for, I will filter down by unselecting everything and then selecting work, energy, and power. And I think this also includes momentum. So this shows 9 results. Now, this isn't all the simulations that are available, although I think all the simulations I want you to demonstrate are here. If you want to see more simulations, especially their legacy classic simulations that's been around a while, you can unselect HTML5. HTML5 simulations are great. They run basically everywhere. But some of the, so let's see which ones popped up. Oh, I think you are going to see me use nuclear fission towards the end of the semester. It's a Java simulation, and they've modified it so that it'll run on a web browser. But I think because it's not HTML5, they are still kind of not displaying it as the first thing. And I think I was looking at this earlier with the motion category also selected, but I don't think any of these additional simulations that relate to motion are ones I want to demonstrate today. So let me just unselect that. And let me just mention a few that I think you might want to look at on your own, and then I'll go into a little more detail with one of the simulations. So one of them is this energy skate park. You know, I've seen this forever. They had a classic version of it, and there's a newer version of it, HTML5 version. And I frankly don't know what to use it for. I've never used it. You're welcome to take a look at it and play with it if that suits your fancy. I will click away from here for now. But that's a energy simulation. I think it illustrates the key concepts. There's energy forms and changes. This we might come back to this when we do thermodynamics because it relates to that more than the mechanical energy we are dealing with right now. Although, let me just check. Yeah, I think this is more thermodynamics oriented. Yeah. So we'll come back to that. I think I might actually have old lecture videos that use older version of that. So what I want you to actually spend more time with is masses and springs simulation. So let me open it, but I'll go to that later. And the other simulations that you might find useful are pendulum lab. I do think I use this later on when we get to oscillations. There's even some homework questions that use this. So so you will see this again later on. But before that, right now, nothing stops you from looking at the simulation on your own. And I haven't really looked at this Hooke's law simulation. I guess I can open it and see. I wonder if it'll have a different content from what I'm gonna do with the masses and springs. This might be just illustrating. Let me just mute the sound thing. About this might be more forces oriented, possibly. So yeah, I mean, there's that. I don't see any energies shown. And oh wait, there's an energy tab, so I'll look at that. This could be useful for physics 4A. Sometimes we combine springs, either parallel or in series, and how to deal with it. That can be actually fairly useful. Let me look at energy. And yeah, I think we can do better with the masses and springs simulation, so let me go to that. I can imagine this being more useful in physics 4A class. So so I think that's all the simulations. Now, some simulations you will see like two versions. There's Energy Skate Park Basics, and there's Energy Skate Park. I have looked at those pairs, and I've never really seen the distinction. And I thought there was a masses and springs basics simulation too. Maybe that's under motion. I never really saw the big difference between ones that are labeled as basic versus ones that are labeled as not being basic. Maybe the controls are easier, I'm not sure. But since here you are welcome to play with it. But since here I'm just talking, illustrating some of the concepts that you can illustrate with the simulations, let me just do the regular version, not the basic version. So masses and springs. This is the simulation. Let me run. I don't think. No, I think you have seen me use this simulation in one of the earlier lectures. I think when we are talking about Hooke's law, spring force. So it's the same basic setup. You hang a mass and it kind of oscillates. You hang a same mass, both 100 grams. Let me stop this. And if the spring constant is larger, it's stiffer. So there are actually kind of interesting differences that come from that. We will get to that more when we get to oscillations. For now, let's look at energies. And I think for that, I'm pretty sure that tab will be useful. Let me just to make sure there isn't something still useful from the vectors. Oh, I guess this what shows you the force vectors. Yeah. Vectors tab or the lab tab that I might want to use. Oh, lab is probably like the most complicated of all. Let me see difference between energy and lab. Interesting. So lab has a period trace which actually can be useful. So if you're hanging it, letting it oscillate, yeah, it shows a period. Let me just do energy, just so it kind of matches everything. So I do believe the main value of simulation is that you can try this on your own. Like there are things that we were wondering about, but I'm not exploring it right now. You're not limited by that. You can just simply launch this simulation yourself, go to this link, or go through the homepage and you can try those things out yourself. If there are any questions, let me know. I'm happy to answer questions. So here, I can hang this 100-gram mass, see it oscillate for a bit, and I think this is one of the things I like doing with the simulations, especially first couple uses. I want to make sure it kind of makes sense to me, that how it behaves. It feels like a fairly faithful approximation of the real world. And this looks like that. I've hung masses on the classroom springs that you sometimes see me use in lectures, and I've seen it oscillate, eventually comes to a stop, and this feels like it's doing it. Now, so one of the things that simulations will offer is it can offer some explanations to some of the things that kind of come in as a part of idealization. So we say mechanical energy is conserved. We say energy is conserved. But here, without great deal of idealization and approximation, it doesn't actually look that way. And in fact, when I talk about in the intro to energy concepts, I kind of ask you to imagine the first couple oscillations kind of continue forever instead of dying down like this. And on the left-hand side, you see the energy graph. That's where you see those kind of explanation of what's happening behind the scenes. So when I pull this mass down, the first thing that you will see is that, I guess overall increase in total energy, what they are labeling as the PE graph and PE elapse are doing, that's a little bit complicated. I'll go into some of those complications a little bit later, like one is decreasing, the other is increasing. And when I'm going the other way, I can actually make the spring force increase, spring potential energy increase. But I pull it down, it starts out with some total amount of energy. And as it begins to oscillate, I'm gonna hit the slow tab so that I have more time to talk. As it begins to oscillate, you see the kinetic energy fluctuating. So at moment of motion where the mass is moving faster, kinetic energy is larger. And actually the total of the potential energy is at a minimum there. And now as it oscillates and eventually comes to a stop, what you are seeing happening, and you saw this actually happen at the very beginning, this grew pretty quickly at the beginning, the thermal energy increases. So what this simulation is telling you is that as this oscillates up and down, the reason mechanical energy is being reduced to a minimum value that you see here, like where you see the top of that light blue color, that's the minimum potential energy that this system can have. And the additional energy that I put in pulling down the mass, the simulation is telling me that's accounted for by the thermal energy that those mechanical energies converted into. And that's the kind of explanation I can also give in a classroom demonstration, classroom lecture. Now, one thing that's nice about simulation, this is a virtual world. Everything here is programmed in. And by default, they put a little bit of damping in so that this looks realistic. Now, once you are trying to get rid of damping, you can get rid of it, mathematically. Make the damping none and see what kind of behavior you see here. You pull the mass down a little bit, you let it oscillate, and mechanical energy is conserved. We have achieved a system where the total, where the conservative forces are the only forces doing any work. In fact, in this system, there are only conservative forces, because as you've seen me draw diagrams of when I was demonstrating this before, you only have gravity and spring force, both conservative forces. So in that, that is kind of annoying, sliding up and down. So in that world where you only have conservative forces, mechanical energy is conserved, and that's what you are seeing here. So and I think let me just explain a couple things that I've said in passing. So let me actually stop this simulation here. So I've said that there are points of motion where kinetic energy is at a maximum. That must be where this is moving the fastest, and the potential energy is at a minimum. Now, I think looking at this, you might think that that point corresponds to where the like elastics potential energy is at a minimum. But you will see that that actually isn't the case. Let me just so if I try to pick a moment in time where the elastic potential energy is zero or close to zero, that's not actually the point where the kinetic energy is at a maximum. That point actually goes past that. Kinetic energy reach the maximum somewhere here. So elastic potential energy is actually fairly substantial. And this is the kind of the complicated a bit. In Physics 4A, I actually have a separate lecture video justifying my particular treatment convention with the vertical springs, basically combining both the gravitational and spring potential energy and treating it as one quote-unquote spring force and quote-unquote spring potential energy. It has to do with equilibrium. So let me mark equilibrium here. And let me increase the damping and just to let this whole thing come to rest. At normal speed probably. So when it comes to rest, then you can see that this is the position where the mass is at rest. This is the mass equilibrium. That depends on where, that depends on how much mass you have. So with 100 grams, this is where the equilibrium is. With oh well, that's tiny. With like 200 grams, this is where the equilibrium is, and you know, it depends on how much mass you hang, because this is the position where let me show natural length. So this is the natural length of the spring. This position is when you've displaced it by this much, is where when the force due to gravity is balanced out by the force due to spring force. And that's why when the mass is larger, it sags a little bit lower. So let me go back to 100 grams. It should be about half of the displacement before. That's a Hooke's law. You know, spring force is proportional to displacement. So with half the mass, half the weight, you only need half as much spring force. So this combined mass equilibrium position, that's the position where the net force is zero. That's the equilibrium position. And that's the place where the combined gravitational and spring potential energy will be at a minimum. And you can see, let me pause the simulation, see what it does. Okay, good. So it's still updating the figure on the left, so I can pull it down a little bit. So you can see, if I pull the mass down a little bit, then gravitational potential energy decreases. But spring potential energy increases enough that the total potential energy is not actually decreasing. As I continue to pull this down, you can see that it's increasing. Can I move the movable line? No, I can't move it there, so never mind. Total potential energy increases. And as I move this up, you can see gravitational potential energy is increasing, but spring potential energy is decreasing enough that it's that the overall potential energy is actually decreasing up until this point here, the mass equilibrium line. And as I continue to raise it up, now the elastic potential energy is decreasing, but it's not decreasing enough to counter the increase of the gravitational potential energy. So as I continue to raise it up, the total potential energy, gravitational plus spring potential energy, actually increases. And after a certain point, so you know, this in a physical setup, at some point I wouldn't be able to actually push on the spring, because a lot of the springs in the lab, they only stretch, they don't compress. But this mathematical spring, you can compress it. So when you raise it high enough, both the elastic potential energy and gravitational potential energy increases. So so this is the equilibrium position. That's the position where you have minimum total potential energy. And so if I start the simulation from here, it wouldn't do anything. It's at a state of minimum energy. There's not enough energy to move. But if I displace it either direction, either raise it a little bit or lower it a little bit, then it'll oscillate. And there's, I guess in this scale, the kinetic energy is so small that it doesn't show. yeah, I don't know if there's a way to do better other than zooming is super and just getting rid of the losing the potential energy scale. But maybe this will be a little bit better. So here, let me slow down the simulation and I can kind of max out the scale here. And when I let go, then yeah, this is what you see. So the total mechanical energy remains constant. Here, it's total and it's the mechanical energy because there's no thermal energy portion. In a little bit, I'll increase the damping and let thermal energy take over the rest. And with in this setup, with the same constant total energy, you see these different forms of energy change. And it's quite complicated interaction. To describe this fully mathematically, you need differential equations. In physics 4A, we only really get to this towards the end of the semester when people have had a more exposure to calculus, and we're not gonna do any of that. But you know, the wonderful thing about simulation is that you can explore these things, these conceptual ideas, without getting bogged down in math. So that's what I want you to demonstrate. Let me just increase the damping a little bit so that some of this mechanical energy will turn into thermal energy. So our belief, and that's what the simulation represents, is the total energy remains conserved. We do not think the mechanical energy simply disappeared when this mass comes to rest. We believe that turned into thermal energy through the friction of forces, through damping. A lot of it goes to thermal, as in heat, things warming up. Sometimes it goes to sound energy. And you know, to verify this experimentally, that's quite a difficult task. Most instructional lab setup is not good enough, not well insulated enough for us to demonstrate this. But this is our belief, and you know, when we have been able to check it, it has turned out to be correct. And based on that experience, even in situations where we are not able to check it or we are not bothering to check it so thoroughly, we still believe that it is the case that the total energy of the universe is conserved. Mechanical energy may change as some of that energy is converted into other forms of energy, and we'll talk about that more when we get to thermodynamics in Unit 3. In the meantime, in situations where we've made sure that conservation of mechanical energy applies, only conservative forces acting, then it's a great principle to use. You can kind of relate potential energy to kinetic energy easily through the conservation of energy idea. Thank you. Bye. As I was saying at the beginning, as you will see with this Unit 2 material, it now becomes what this course should be the entire semester. It is a conceptual physics class. We try to use as little math as possible, and you see that promise fulfilled in Unit 2. As we are talking about energy, momentum, you will see most of the questions become much more conceptual, so that you don't have to look at kinematics equations that involve square. Well, yeah. So having said that, I have seen people. So all these first 11 questions or so, most of that is reading the chapter, and that's kind of why hint kind of says review the chapter and applying the formula that's given there, plugging in numbers. And I found most people, I haven't seen people struggle with it too much, but where I have seen people struggle at are these later questions. The multi-part questions, where I can see that it's multi-part because it's more than 1 point. So let me pick 1 or 2 questions here and go over that, so that because even though those questions, they are numerical, but they are meant to be conceptual, and they are conceptual. So I want you to have this chance to illustrate that. So I think this is still application of formula, and I do kind of do the algebra for you, and you can plug in the numbers there. Let's see. I think question 13 is where I have seen people struggle. So let's look at that. I guess that actually didn't give me much more space. Because I think I do try to guide people through in the hint, but I don't know. I think maybe part A is getting people to think the wrong things. I don't know. So let me. So I'm gonna be writing on the screen to kind of let's just work through this question. So the question says a shopper pushes a grocery cart some distance at a constant speed on level ground. And there are some formulas that you are going to be using. Let me write them on the screen because at this point in the so people who are here in real time, you might not have read the chapter yet, so you will, I think. So let me write down the formulas that I'll be using. That's in chapter 4. So one is the definition of work, which is defined as force times distance. So it's good that I have distance given here, which I guess I'll be needing. And the other formula that we'll have some idea of is the formula for kinetic energy. That kinetic energy is given by 1/2 times mass times speed squared. And the reason I want you to highlight this now is because the question told us that the grocery cart is moving at a constant speed, and that's meant to give us some information that we'll be using throughout at some point in this question. So part A is meant to be a simple application of formula that's given. We know from the chapter that the work is given by force times distance. We have distance, and part A now gave us the force. So to calculate work, really all we have to do is, okay, work is force, 20 newtons, times the distance, 21.6 meters. And oh, I think I can do this one in my head. So 432, I think 432. It's a Newton times a meter, and when you read the chapter 4, they define a new unit of work, new unit, which is a unit of work called joule. Which is this unit here. So it should be 432 joules. Let's see if that's correct. If it's not correct, it'll be embarrassing. And I guess, so you have unlimited attempts, and you can use that fact to kind of try one part at a time. It'll mark the other parts as being wrong, but that's fine. You have unlimited attempts. Use that unlimited attempt to make sure you have gotten earlier question correct, so that as you move on to the other part, you have some assurance that you did this correctly. Okay, I'm trying to line it up. All right, so the shopper does 430 joules of work as the shopper is pushing on the cart. And where I have seen people struggle with is in part B, which asks, what is the net work done on the grocery cart by all forces on it? And I think, I guess, so it's meant to be a conceptual question. And people, I think, get distracted by all these numbers that they have seen. So, the concept that I'm referring back to, which I think is referred to in the hint, which refers obliquely to the consequence of network described in section 4.2. For those people here, let me give you what that consequence that's highlighted in the section is. The consequence is that when you have net work, that results in change in energy, And specifically, especially if you are looking at network done by both applied force and basically network done by all the forces, then the change in energy comes down to change in kinetic energy. So this is the concept that's very useful from that section 4.2. And that's why I was highlighting this information at a constant speed. Because if the cart is moving at a constant speed, then you know from the formula for kinetic energy, where V doesn't change, mass doesn't change, so change in kinetic energy will be zero if it's moving at a constant speed. So without having to do any additional math, you know that the net force must be zero, because with all the forces acting on the cart, including the applied force by the sharper, the kinetic energy of the cart didn't change. So the net force must be 0 joule. Let's check. And that's the correct answer. And I think you actually had a version of a question that's similar to this in chapter 3. I think that question before you or properly introduced to friction. And so at this point, you actually do know about friction, so it's not new. And so part C reconciles these two things in A and B. In A, you recognize that the sharper does work, force times displacement, that's 432 joules of work. In B, despite all the work being done by sharper, the net work being done on the cart is 0. So something is doing negative work, so that all the work done adds up to 0. So without knowing the amount of friction force, you know that, well, the work that the friction force does exactly cancels out this work. So must be minus 432. And that's the correct answer. So this question, there is some amount of math involved using the definition of work. But once you have done that, then the rest of the question is conceptual. All right, any questions on that? Oh, no questions. All right, let me clear this. Don't remember quite if there were other questions that people have struggled with in the past. This question is quite similar to question 13, so I think people do fine. Question 15. I guess it's adding a bit of complication. I think once people get the concept from question 3, then 15 isn't too hard. Here with friction force, instead of telling you that the shopping cart is moving at a constant speed, here actually shopping cart speeds up. And so you are actually just given the magnitude of the friction force. So maybe I should go over it. Let me go over it, because I think the type of calculation you go through here is different enough from question 13. So as usual, these hints are meant to be helpful. So I do strongly encourage that you take a look at it, and you can read it as you're going through it. And let me also do this in the video form. So this is how you approach this question. Once again, I'm going to be using the definition. I'm going to be using the definition of work, force times displacement or distance, and the relationship between the net work and the kinetic energy. That net work gives the change in kinetic energy, and that kinetic energy is given by 1/2 times mass times speed squared. And in the hint, I do this calculation that you can reverse this relationship and solve it for speed. And when you do, speed will be 2 times kinetic energy divided by mass square rooted. So these are the formulas that I'll need to use. So the question gives me the amount of force that the chopper is applying, 8 newtons, over the distance, 1.2 meters. So that gives me a way to calculate the work that the chopper does. And that amount of work done is with 8 times 1.12. I think I can do that in my head. So that'll be 9.6 joules. Well, let's check. Good. Let me scroll down, line it up. Am I lined up? Okay. So, all right. And if the shopping cart rolls frictionlessly, meaning that the applied force 8 newtons here is the only force, that is the net force. So this is the net work done. This does give you the change in kinetic energy. And I guess we would be assuming that the kinetic energy is changing from 0. So this amount of work should be equal to the kinetic energy at the end. So in this formula here, I know the kinetic energy now. It's 9.6 joules. So I do the rest of the calculation. 2 times 9.6 joules divided by this mass given here, square rooted. That should be the speed. And I can't do this one in my head, so let me use the calculator so that I can actually do it here. Calculator. All right, 2 times 9.6 divided by the mass, 20 kilograms. So that's the thing under the square root. Let me take the square root. So it's 0.979. I'll round it to 3 significant figures, which gives me 0.98. So all the units should work out so that I do have meters per second in the end. So 0.98 meters per second. Let's hope it's correct. One of these times it will be wrong and it'll be embarrassing. Okay, so in the above scenario, it turns out the shopping, okay, so in part to be the important thing to recognize is that it's changing the setup. So some things are remaining the same. The force that the shopper is applying didn't change, one. But now it's saying that's not the only force. There's a friction force acting on the cart also. And there's that 3 Newton of force. So sometimes it does help to draw the force diagram here. You don't necessarily have to, but let me draw it. So what the forces on the cart looks like is you have the applied force from the shopper. That's still 8 newtons, but now there will be a friction force that's going to be opposing the motion of the cart. So as the cart is moving to the right, in the direction the shopper is pushing, this force here is going to be doing negative work because the direction of this force is opposed to the direction of displacement. So there are different ways to do this calculation. Let me do the way I like because it's going straight to the energy. So I'm just going to calculate how much negative work this friction force does. So that's going to be, so work done by friction force. That's going to be the amount of force. And let me just give it the minus sign here. So minus 3 newtons times the distance is the same, 1.2 meters. 1.2 meters. So I can do this one in my head. It's going to be minus 3.6 joule of work. So in the changed scenario in part B, now the net work is not going to be 9.6 joule, but now let me write it here, net work will be, well, the positive work done by the shopper, 9.6, minus the negative work done by the friction force. 3.6 joules. So the net work done is 6 joule. That's how the answer is changing. Now I need to redo the calculation that was done here. So plug in this value of 6 joule for the same calculation we did here, and we should be able to get the new velocity. So let's put that into calculator and do that. So 2 times 6 divided by the same mass, 20, 0.6, that's the thing under the square root. So take the square root, I get 0.77 rounded to 3 significant figure, so 5. So 0.775, let's hope it's correct. And so, it's once, if there's a friction force, then the speed of the cart is slower than it would have been without friction, which I hope makes intuitive sense. All right, let's keep going. By the way, if there are questions, you are welcome to just ask. I mean, it will be recorded, but you are welcome to just ask after having unmuted your microphone, or I guess not. You can also type it into the chat. Now, to continue on PhYS, new scenario, and and what I want to highlight is, and I think this is where people might have, because I think, well, I do it differently sometimes. Sometimes when you have multi-part questions like this, each is like in sequence. This question, each one is new. That's why it's saying new scenario, change your things, redo the calculation with a change the setup. So here, it's the way it's changed. Instead of having a sharper push it, now it's just rolling down a ramp. So you don't have someone that's doing the work, but you don't have someone, but you have something, gravity, that is still doing work. It says 31 joule of work. And 31 joule is 31 joules, whether it's being done by a person or if it's being done by gravity. 31 joule is 31 joules. So we can go through this exact same calculation here, just with a new number of 31 joules. So let me do that. So it's the exact same calculation. 2 times 31 divided by 20. So this is the quantity under the square root. Take the square root, 1.76 meters per second. 1.76 meters per second. So that's it. So these multi-part questions at near the end of the problem sets, they are a bit more involved, but they are still conceptual. I make sure to use the hint, because once again, I do try to be helpful in the hints. So what I'm going to try to do is go over kind of the other questions. Now, the types of question I will just display and skip are questions like these. These questions, there's a hint, and to tell you the truth, they are kind of multiple answer or multiple choice questions. And I think even if you're struggling, you can eventually get to the right answer. I'm happy to explain why the right answer is right. But this is where you can go quite a bit of way through trial and error. So I'm going to skip all these questions, even the ones that are covering concepts that people frankly struggle, like situations below where no work is done. It can get quite complicated because we are relying on the physics definition of work, which is very unintuitive to a lot of people. So acknowledging that, for now, I'll skip it for the purpose of this video or virtual class session. And what I want to do is spend maybe next 15 to 20 minutes working through some of the questions which are numerical, where you have to plug in numbers, and that's where you can't just keep guessing. You kind of have to know what you're doing. So let me start out with the question 10. This is, I think, a lot of people do get this kind of on the first try, but it's a good warm-up question. So let me start out with this. It says, calculate the work done on a crate
pushed some distance up along a ramp as shown in the figure below. The man exerts a force of 220 newtons on the crate parallel to the ramp, and the crate moves at a constant speed. Most of the time, well, all of the time, I ask you to look at the hint, and it says check the section for the definition of work. And most of the time, even when I'm kind of sounding a bit vague and mysterious, I'm trying to be helpful. So I would recommend following the hint. It says check the definition of work. So what I hope you did is you looked at the section and you found this definition of work. That work done is force times displacement. That's the definition of work. So that ought to be useful. You are asked for the work done by the man on the crate. Well, for force, you are told how much force that the man is exerting on the crate. You are also given the distance and of 3.1 meters up along the ramp. So, all right, let's multiply. That seems like I'm all set. So let me do force times distance. Let's see what we get. 220 times distance, 3.1, is equal to 682. So 682 joules. I get, okay, that's correct. Now, there can be some subtleties or finer points that could come up, and that sort of what some of the multi-answer questions earlier were getting at, in that the relative direction of the applied force and the displacement matters. But this question is set up in a simple way. I'm not trying to be tricky. I'm just trying to get you to look up the definition of work. So this question, fill in the blanks in the below statement. It's basically a number plugging in exercise. Let me just go through this quickly. It kind of does that, review the section for the formula for kinetic energy. And there's a reason I'm saying that. When you look at the formula for kinetic energy, this is what you will see. Kinetic energy is equal to 1/2 times mass times speed squared. So for each of these scenarios, you are kind of given all the numbers. You are given the mass, you are given the speed, so you just plug in the numbers. The one thing you might have to watch out for is this, the power of 10. So let me kind of watch out for that. Let me start by plugging in numbers. So I guess I can put it here. Sorry, there. Yeah. So let me just plug in the numbers for the truck. 1/2, it's 0.5 times the mass, 21000 times 36. And then I have to be careful here. So this is where you kind of should know how your calculator works. For this Windows calculator I'm using, I know if I push this button now, then this square will apply to 36 alone. Different calculators do this differently. You should know yours. So squared, you can kind of see it here, is equal to, oh, that's a big number. And that's actually why I have this times 10 to the 6 joules. So I don't put this whole thing in. If I were to do this, 13608,000, it'll say it's wrong. And it's wrong for a very simple reason, that the answer I gave is basically 13608,000 times another 6 zeros, 10 to the 6. So that's not the correct answer. What I really need to do is I need to take this answer and kind of try to figure out how to put the number into this blank so that the combined number is equal to that. There's a kind of one easy way to do if you are familiar with the scientific notation and you feel comfortable with dealing with these numbers is you can kind of recognize that this 10 to the power of 6 is basically adding 6 zeros. So I can actually kind of go backward here. I can, starting from the decimal point at the end here, and kind of move back 6 decimal points. 3, 4, 5, 6. So if I had a 13.6 times 10 to the 6, that should be the same number as this. So I can do 13.6. That gives me a correct answer. Now, sometimes this like power of 10 is big, like this next one here, 10 to the 9. I guess I could count to 9, but maybe I don't want to. Then one thing you can do is you can kind of do a unit conversion. And in the interest of time here, I'll just do a quick thing. I can just divide this number by 10 to the 6, and that'll tell me what should go in front. Because that'll give, when I divide by 10 to the 6, the number I get is the number to which if I multiply 10 to the 6, then I'll get back this. So I can divide. And here, instead of 10 to the 6, literally, I want to do this. I have this button in my calculator. So I think the way I do is I type in 6 first and then this. Yeah, then it's 10 to the 6. So I get 13.6. That's what the number was. Let me do the second number this way. So it'll be another 1/2, 0.5 times the mass, 60 kilograms times 6,200 meters per second. That's a large number. I'm not going to worry about it right now. Squared. When I type in equals, that gives me, okay, 0.5 times 60, 62 squared. All right, I get that huge number. I guess that's why I have this times 10 to the 9. So let me divide it by 10 to the 9. Verify that. Type in equals. I get 1.15. So that must be the correct answer. And I recommend with all these number questions that you type in at least the 3 significant figures. That will make sure that you are okay as far as rounding goes. Comparing the kinetic energies of the two of them. Well, the astronaut, it's larger number, so the astronaut has larger kinetic energy. I don't think there's ever a scenario where it's going to be truck, the way the numbers work out here. So this is a kind of question where it is easy to answer, plugging in the numbers into a known formula. But with a lot of students in Physics 10, you might not have had that practice, a lot of that kind of practice. So I hope what you see here at least gives you kind of some hint into using your calculator. Now, sometimes calculators are frustrating to work with. How physical calculators work sometimes can be very unintuitive. Then one kind of tool that I recommend that you know where it is online tool, Wolfram Alpha. It's a basically online calculator, but it's more advanced than even Google is. It's very good at doing calculations like this. If I do calculations like, let me just plug in 50 kilograms times 40 meters per second squared. It does the calculation like you can do with your calculator. It also knows how to work out the units. You see that it gives me one of the answers in joules because it's smart enough to work out the units and figures all of that out. And so this tool is useful if you're particularly struggling with how your calculator works. All right, any questions on this question?